but just ignore the free. This is Gibbs energy on this axis. If we go from our reactants, so our pure reactants here on the left, all the way to pure products on the right, Going from left to right all the way would be the reaction going to completion, Complete conversion of reactants into products. And we see that there is a positive delta G associated with going from here, from our very start of just reactants, to here, our very end of just products. If this is a positive delta G, will this reaction go to completion? Shake your head no, or shake your head yes. Will this go to completion, this reaction, if we have a positive delta G associated with it? Seeing some hesitant no's. No, right? We know that if delta G is positive, it's not going to be spontaneous. This reaction, though, it will happen a little, right? It still wants to get to equilibrium. So if we start with only reactants, I start at this point here, it's going to move in the forward direction until it gets to equilibrium, and then it'll kind of equilibrate, or kind of stop there, right? It doesn't want to go all the way to completion because there's a big positive delta G here. Now let's look at this funky curve. Okay, here, where is my equilibrium point? My equilibrium point is the lowest point on the graph, right? So it's the equilibrium is right here, right near pure reactants. So in this example, there will be almost no reaction happening because my equilibrium is so close to the start where we only have reactants. And that makes sense if we look at the standard delta G of our reaction, because look how big it is, right? There's no way we're going to get all of our reactants becoming products, all of the reactants going to completion, right, to products, because look at this huge positive delta G. That's very, very much not spontaneous. And if we look at the opposite here, where we start with our reactants up here with high Gibbs energy, and my equilibrium point is right here, right near the end, we've got a huge negative delta G, right? Going from my reactants up here all the way down to my pretty much my products over here. We're decreasing our Gibbs energy a lot. A big negative means we have a spontaneous reaction, and this will basically go to completion. Now you'll note that pretty much no reactions fully go to completion. Probably still have a couple of molecules of reactants left, even in a reaction like this with a big negative delta G, but we say it goes to completion because it almost does. Okay, any questions about these graphs? These things I find the more you sit with them, the more you think about them, the easier they get to process what's going on. So let's just compare quickly our standard delta G, so our Gibbs energy of our reaction, with the K. And recall that last class, we learned this reaction, or this equation. Delta G naught is equal to minus RT ln K. Right, so we have a relationship between delta G naught and our K value. If we have a very, very big positive delta G of reaction, this is like this graph, right? Really big positive delta G. What happens? There's pretty much no reaction happening. We have pretty much all reactants left in this. When we have a really big positive delta G, we end up with a very, very, very small K value, a small equilibrium constant. And what does a small equilibrium constant mean? It means that almost no reaction happens, right? We're pretty much left with all reactants at the end, because not much of it wants to react. On the other end of the spectrum here, at the bottom, if we have a really big negative delta G, so this guy here, going from reactants to products, we really decrease our delta G, that means we're going to have a really big K value. What does a really big K value mean? Really big equilibrium constant? Big equilibrium constant means we're going to have a lot of that reaction happening. We're going to be forming a lot of products. And so when we have this big K, our reaction pretty much goes to completion, or the product are heavily favored because the reaction is really happening a lot in the forward direction. If we have a moderate delta G, so kind of not a huge positive or not a huge negative delta G, somewhere in the middle, we're going to have kind of a moderate K. And so if we are doing that reaction, when it sort of stops, so to speak, we're going to have a mixture of products and reactants because it's going to come to equilibrium, right? So we're going to have some sort of combination of both our reactants and our products. And that's what we'd see here, right? Equilibrium's here, so our reaction sort of stops here. And if we go down to the extent of our reaction, we see we're going to have some reactants, we're going to have some products in this example. Okay, now we've been talking about delta G naught, so our standard delta G, and just regular delta G. But what is the difference between them? Well, let's start with delta G naught. Delta G naught is a constant for a given reaction. Remember that to calculate, or delta G naught can be calculated based off of delta G formation values in tables, right? So without doing any chemistry, without reacting anything, we can calculate delta G naught for a reaction, which means that it's kind of like a property of the reaction in the same way that your equilibrium constant is a property of that reaction. But technically, delta G naught refers to the Gibbs energy change for a reaction or for a process where all of my reactants and all of my products are constantly in their standard states, which technically would mean, say we have an aqueous reaction, all of my reactants and all of my products are all 1 molar, right? That's their standard state for the whole reaction. But does that really make that much sense? No, right? Because if a reaction's going to happen, we can't maintain the same concentration of 1 molar the whole time. Some of my reactants are going to get used up, some of my products are going to get produced. What it really tells us, it kind of gives us a way to compare different reactions and see if they would be spontaneous under standard conditions, even though a reaction under standard conditions, like maintained standard conditions, can't really happen. And you might be sitting there thinking, well, that's nice, but why the heck do we have this then? Like, what's the point? The value in delta G naught really lies in us being able to calculate K for virtually any reaction. So I'll just write that equation back on the board here, that delta G naught equals minus RT ln K. K is a really important value for us as chemists because we want to know how much of a reaction is going to happen, right? We want to know where's the equilibrium point. And without measuring anything, without setting up an experiment, without using materials, we can just use our tabulated values from our textbook to calculate the standard delta G or delta G naught for a reaction. And based on that value, we can calculate what the K would be for any reaction we want. And then going into a lab and getting our experiment set up, we already know what to anticipate because we've calculated K. Delta G represents kind of how far we are from equilibrium in a reaction, right? Delta G here without the little circle, without the not symbol, is delta G under non-standard conditions. So let's go back to our graph here. Delta G is how far you are from equilibrium. So let's just say I'm over here on this graph. My delta G is the distance from wherever I am, say I'm right here, to that low point in Gibbs energy. If I have a really big delta G, that means I'm farther from equilibrium, right? Oops. If I'm right here, if I'm really close to equilibrium, and I have reactant and product concentrations that are almost at equilibrium values, there's just going to be a small difference in Gibbs energy between where I am and the equilibrium point. But let's just say I'm looking at this graph, and I'm over here, and I have mostly products. My delta G to get to equilibrium is going to be really big because I'm far away from it, right? Right here I've got mostly products, but my equilibrium is mostly reactants. So the delta G associated with being at this point in the reaction near the products means that I'm quite far from my equilibrium and thus have a bigger delta G. Okay, so a bigger delta G, whether it's positive or negative, means there's kind of more of a driving force for that reaction to move in the forward or the reverse direction, whatever's going to get it closer to equilibrium. If it's a small delta G, means we're actually pretty close to our equilibrium values. Okay? When we actually get to equilibrium, our delta G is 0 because we are at our lowest Gibbs energy point. Okay, let's do some fill in the blanks. And these I did not post the answers, so you're going to want to write these down. Let's say we have this reaction of A plus B becoming AB, and they give us the standard Gibbs energy, and that's minus 22 kilojoules. Question A asks us, to fill in the blank here, this reaction is spontaneous in the what direction? If you think it's spontaneous in the forward, give me an up signal. If you think it's spontaneous in the reverse, give me a down signal. Wait, I'm mostly seeing ups from the people that are voting, which is great. Yeah, this is going to be spontaneous in the forward direction. So anytime you're given a delta G value alongside a chemical equation, this is for the reverse direction. So if this is negative, it's spontaneous in the forward direction. If this were positive, it would be spontaneous in the reverse direction. Okay, as the reaction proceeds, delta G naught, what? Does it increase, does it decrease, or does it stay the same? I don't know how to ask this one in hand signals. If anyone wants to give it a guess, please raise your hand, but if not, I will tell you the answer. Well, delta G naught, as we saw on the previous slide, that's a constant for a given reaction, right? So as the reaction proceeds, delta G naught stays the same. Doesn't matter what state, what conditions we're in, our delta G naught associated with a standard reaction is always the same. It's a property of that reaction. Okay, in this example, will the equilibrium favor the reactants or the products of the reaction? If you think it favors the reactants, give me a point up. If you think it favors the products, give me a point down. Awesome, okay, I'm saying point down, that's right. Because we know that this will spontaneously move in the forward direction, right? If you start with equal parts reactants and products, this will move in the forward direction, which means it's gonna make more of the products. At equilibrium, what does delta G not equal to? Anyone want to take a stab at this one? This is another trick question. It stays the same, right? It's a constant. We're just asking this twice to really drill home that this stays the same the whole time. This is a constant for my reaction, so it's still minus 22 kilojoules. At equilibrium, what is regular delta G? Delta G at non-standard conditions equal? That equals 0, right? Because we're at that lowest point on the curve, we're at the lowest given energy level, we're the happiest, most stable part of the reaction. Okay, a few more. Under standard conditions, what is delta G equal to? I'll let you think about this one while I write something on the board. Okay, under standard conditions, what is Q equal to? Under standard conditions, Q is equal to 1, right? Our reaction quotient is equal to 1. It's because our pressures under standard conditions are 1 bar, and our concentrations under standard conditions are 1 molars. Q is equal to 1 under standard conditions. And remember that ln, the natural log of 1, equals 0. That means that when Q equals 1 in this expression, this whole thing is equal to 0, because 1Q is equal to 0. And so under standard conditions, what is delta G equal to? It's equal to delta G naught, which is minus 22 kilojoules. You could have just reasoned that out also in your head. You don't have to show the calculation there. But under standard conditions, delta G is standard delta G, okay? The further from equilibrium the reaction is, the what? The magnitude of delta G. So if we are farther from equilibrium, is my delta G larger or smaller? If we are far from equilibrium, give me a point upwards if it's larger, give me a point downwards if it's smaller. If we are far from equilibrium. Okay, the fingers I'm seeing are pointing up, that's right. If we are far from delta G, or sorry, if we are far from equilibrium, our delta G is gonna be bigger. It's got farther to go to get all the way down to that low point of equilibrium on our curve. When QP here equals 1, this is just our reaction quotient using pressures. I could have gotten rid of the P, but I did not, and here we are. So when QP equals 1, when we're at standard conditions, what is delta G equal to? Well, this is kind of the same question as F, right? We can plug in 1 over here for Q, ln of 1 is 0, which means that this whole term is 0. And so when Q equals 1, delta G is equal to delta G naught. If our reaction quotient is equal to our equilibrium constant, what does that mean? Well, that means that we are at equilibrium. And if we are at equilibrium, you can show me this one with your hands. What is delta G if we are at equilibrium? You can make the number on your hand. That's my hint to you. Awesome, I'm seeing some zeros, that's right. When we're at equilibrium, so when Q is equal to K, delta G will be equal to 0, we're at our lowest energy point. And lastly, the equilibrium constant for this reaction is, I had a typo here in your slides, this is not supposed to be 0, it's supposed to be a 1, so just make sure you change this to a 1. We can't have a negative equilibrium constant, it can just be less than or greater than 1. So for equilibrium constant here, if we look at our negative delta G, do we think that our equilibrium constant is less than 1 or greater than 1? So give me a point up if you think it's greater than 1, a point down if you think it's less than 1. This one's a little trickier. Remember earlier we said that this favors the products, right? And this will move in the forward direction. If it's moving in the forward direction, and we're favoring our products, that means our equilibrium constant will be greater than 1. Right? And I can go back a bunch of slides from these graphs. Here, equilibrium constant is greater than 1. Right? We can see that the forward reaction is favored here. The forward reaction is spontaneous because our equilibrium constant is greater than 1. Okay? Okay, let's get our brains working and do a practice problem. So here we have the reaction here of N2O4 in equilibrium with 2NO2. Both in the gas phase, and we have the delta G formation for both of these compounds. Part A here says to use this data provided, the data on the left, to decide whether this reaction is spontaneous under standard conditions. So what is that? Think about what it's asking you for here. Is it spontaneous under standard conditions? And then B, in which direction will it proceed if these two gases are mixed at 25 degrees Celsius and they each have a pressure of 0.25? So here in question B, we're not under standard conditions anymore. All right, I'll give you maybe till 9:34, 9:35 to give this a try, think about how you'd approach this and what you want to be calculating, and then we'll go through it together. Okay, folks, how are we feeling? Do you want a couple more minutes? Give me a finger up if you want a couple more minutes. Give me a thumbs up if you're ready to go through it. A couple more minutes? Okay. Okay, let's go through this together. So question A here is asking us to decide whether this reaction is spontaneous under standard conditions. Now, anytime we ask you if it's spontaneous under standard conditions, we're asking you, is the forward reaction spontaneous? Will more NO2, or will NO2, N2O4 become more NO2, okay? I know we've been talking a lot about forward and reverse reactions, but the way it's phrased, it's asking us if it will be spontaneous in the forward direction as it's written, okay? And how do we figure that out? Well, we need to figure out what delta G naught is. We know a few ways to calculate delta G naught, but what are we given? Well, we're given delta G formation values, so we're gonna use those to calculate our standard delta G of this reaction. So for part A, my delta G naught for my reaction, it's going to be equal to my delta G of formation of my products minus that of my reactants. So I've got two, stoichiometric coefficient of 2 for my NO2 product, so I'm going to multiply the Gibbs energy of formation of NO2 times 2, so 51.3 kilojoules per mole. And then I'm going to subtract the delta G of formation of my reactant. I've only got one of them, so I'm not multiplying this by anything. So I'm going to subtract 99.8 kilojoules per mole. And that gives me a standard delta G value of 2.8 kilojoules per mole. Is this going to be spontaneous? Yes. Is this going to be non-spontaneous? No. Give me a thumbs up if it's going to be spontaneous. Give me a thumbs down if it's not going to be spontaneous. Okay, awesome. Yes, it's not going to be spontaneous. This is a positive value. So it's not spontaneous in our forward direction because it is positive. Now how about question B? So question B, we are under non-standard conditions, which means that we are going to need to use this equation over here at the top. So for B, my delta G equals my delta G naught. So we just calculated that. That's 2.8 kilojoules per mole. I'm actually going to do this calculation all in joules. So I'm going to right away convert my 2.8 kilojoules over here into joules. I just multiply that by 1,000. So that's 2,800 or 2,800 joules per mole. I hope that's clear enough. And then plus RT ln K. So what's R? We've got 8.314 joules per mole times Kelvin times my temperature. They gave us a temperature of 25 degrees Celsius, but remember that we are always going to be working in Kelvin. So this will be at 298 Kelvin, right? Just 25 plus 273 Kelvin times ln Q. Okay, now how do I figure out ln Q for this one? Well, recall that Q is the same as my equilibrium constant. We set it up the same way. We've got two gases here, so they're both going to be involved in my reaction quotient, right? It's just gases and aqueous substances that are involved in my reaction quotient. And it's going to be my product, which is my NO2, over my reactant. My product and my reactant both have a pressure of 0.25 bars. Because my NO2 has a stoichiometric coefficient of 2, what am I going to do? I'm going to add a square to its pressure. And my reactant has a pressure also of 0.25, but the coefficient is 1 here, so I'm not squaring it or anything. And when you do out this math, and make sure you practice on your own calculator that you get the same answer that I do, you get a value of minus 0.635 kilojoules per mole, or 635 joules per mole. Is this spontaneous? Give me a thumbs up if it's spontaneous, give me a thumbs down if it's not spontaneous. Awesome, the fingers I'm seeing are that, yes, it is spontaneous. We have a negative value of delta G here, so this is going to be spontaneous. I hope you can read that, I know what I'm saying. It's going to be spontaneous in the forward direction because it is negative. Okay, so our conditions can absolutely change whether something will be spontaneous or not. Okay. All right, so temperature dependence. So I mentioned this a little bit, I think last class, that enthalpy and entropy values, they vary a little bit with temperature. So if I'm conducting a reaction at a really high or really low temperature, they're going to be a little different than at room temperature, but they don't vary too much, okay? Delta G, on the other hand, my standard Gibbs energy, we see that delta G is equal to delta H minus temperature times delta S. So from this equation, we can see that delta G varies a lot with temperature. It's like temperature is directly affecting my value of delta G. Because we know that delta G is strongly influenced by temperature, it changes significantly with temperature changes, and we know that my delta G naught is equal to minus RT ln K, because this guy changes strongly with temperature, it means that my equilibrium constant will also change a lot with temperature. So what do we do about this? What if I want to calculate K at a different temperature? What do I do? Well, I have these two equations, right? Delta G naught equals delta H minus T delta S, and delta G naught equals minus RT ln K. I'm just going to take this guy, my enthalpy and entropy, and make it equal to minus RT ln K, since they're both equal to delta G anyway. Then I'm going to do some fancy math, and you do not need to concern yourself with the derivation. If you're curious about this fancy math, it is written out in your textbook. But I'm going to just play around with how this looks. This is the same equation here, just set up a little bit differently. And there's some magic in this equation. And if you don't see it yet, hopefully you will when I start writing. This is set up in the form of a straight line. So what do I mean by that? This is written in the form of y equals mx plus b, which hopefully you remember from high school math. Y equals mx plus b is the expression for a straight line on a curve, right? My y value is ln k. My m value, my slope, is equal to, negative delta h over r. My x value, so what I'd be plotting on my x-axis, is 1 over t. And my b value, so my y-intercept, is equal to my change in entropy over r. Can I get a thumbs up or a thumbs down? How much graphing have you guys done in Excel with things like this, where you're making something a straight line, you add a trend line, you get an equation for the line? Give me a thumbs up if you've done it quite a bit, medium if you've done it but you're not so familiar, and thumbs down if you have no idea what I'm talking about. Okay, I'm getting a mixture of thumbs up and thumbs to the side, which is great. If you go on in chemistry, or a lot of, well, largely chemistry, but I think probably a lot of subjects in the sciences, you're going to do a lot of graphing like this. We love to graph things in straight lines. You won't be tested on this on your exam because you won't have Excel on your exam and you won't have a graphing calculator. But we will get into some plotting like this when we get into kinetics because it will be part of your post-lab report for lab 4. But that's anyways, I'm getting ahead of myself, that's for kinetics, okay? The value of this equation and the value of making it into a straight line is if I have a bunch of k values and a bunch of corresponding t values, I can graph ln k versus 1 over t and come up with a straight line, right? In Excel or with a graphing calculator. It'll spit out an equation for me. And then once I have that graph, I can take any temperature I want and plug it into that equation that Excel has given me and figure out the k value at that temperature. Okay, so this is really helpful when we're trying to figure out k values at different temperatures. Now, as I said a second ago, you guys won't be able to use this or do this on your exam because it's multiple choice without a computer. But what if you just have one k value at a certain temperature? Maybe you know the k value at 25 degrees, and you want to figure out k value at 400 degrees. Is there another way we can do this? Kind of like a shorthand form? Yes, there sure is. This is what we call the two-point version. I haven't told you what this is called. This is called the Van 't Hoff equation. Okay, this equation on the right here, we call this the two-point version. And this you can absolutely do on a test or a final setting, okay? In this equation, you can, if you know my k value at some temperature, T1, and I want to figure out my k value at a temperature, T2, I can plug in all of my values and solve for k2. If you don't like math very much and you don't like working with logs, with lns, with exponents, I really highly recommend that you work through these problems because the ln here and solving for k can get a little bit tricky. If you want extra help, you can do so in office hours. But I highly recommend you do some questions like this one. And on that topic, let's do a question. This practice problem says the dissolution of calcium hydroxide has the following thermodynamic data at 298. So at room temp, we've got our standard delta G of 30 kilojoules per mole, and we have our standard enthalpy change of minus 2.5 kilojoules per mole. It's asking us to use the data that we have here to calculate the equilibrium constant for dissolution for this process at 500 Kelvin instead. So it's a little bit trickier, so I'll just give you 2 minutes to see how you'd approach it, and then we will go through it together. Okay, how are we feeling? Ready to go? Thumbs up? Or need another second? Give me a single finger. Okay, I'm seeing not many things, but I'm seeing some thumbs up, so let's just go through this together. If ever you get to a question on a test or a final, and this goes for really any course where you have math, if you feel overwhelmed by all of the things that you could use right now, you don't know where to start, write down all the variables you know, that's what I've listed here on the side of the screen, and write down what equation or equations you think might be useful to you. Okay, so I know that it's asking me to calculate an equilibrium constant at a different temperature. We only have one equation for that, and it's this guy that I've written at the top of the board, the Van 't Hoff equation that we just learned in the previous slide. Okay, now let's see if I have all the variables for that equation. So I have my delta H value that was given to me, and I'm going to work fully in joules for this problem. So I'm going to right away just write this in joules per mole. So it's 2,500 joules per mole. I hope you can see that. Didn't leave myself a lot of space. Okay. My first temperature is 298 Kelvin. And my second temperature is 500 Kelvin, right? We're trying to figure out K at 500 Kelvin. If we're trying to figure out K at 500 Kelvin, what are we trying to figure out? We're trying to figure out K2, right? Or K at our second temperature, which is 500 degrees, or 500 Kelvin. And what about K1? So K1 isn't directly given to us, but do we know how to calculate K1 based on what we've been given to us? Hopefully, yes, but this might be where it trips you up. So the first thing I need to do is figure out K1. Well, I'm given delta G naught, right? And I know that delta G naught is equal to minus RT ln K. A reminder that I can only use this equation when I'm at 298, when I'm at 25 degrees Celsius. I cannot use this equation at 500 degrees Kelvin, okay? This is only for 298. I can't stress that enough. So our delta G is 30 kilojoules per mole. I'm going to write that in joules, so 30,000, right, multiplied by 1,000 joules per mole is equal to minus R, which is my gas constant, joules per mole times Kelvin, times my temperature, which is 298, times ln K. And when I solve this out, this will be K1. My K1, my K at 298, is equal to 5.51 times 10 to the minus 6. And a reminder, our equilibrium constants do not have units, they're unitless. Okay, great, so now I have K1. Now I can use this 2-point Van't Hoff equation to calculate my equilibrium constant at the higher temperature. And I'll do my best to make this as legible as possible, but definitely be writing along on your screen. All right, so ln of K2, that's my unknown, over K1, which is 5.51 times 10 to the minus 6, is equal to minus, I'm going to add a bracket here so I don't get confused with my signs, so minus my delta H, which is negative 2,500 joules per mole, divided by my R constant, 8.314 joules per mole times Kelvin. And then all of this times 1 over T2, my T2 is 500 Kelvin, minus 1 over my T1, which is 298 Kelvin. And when I do out the math, I get a K2 value of 3.67 times 10 to the minus 6. And as you copy this down, I'm just going to emphasize one last time, it might be really tempting if you're in a test setting and you're looking at the formula sheet to go, oh, here's a way to relate temperature and K and delta G. You cannot use this for anything but 298, okay? As a reminder, as I was saying earlier, my delta G value here, the standard one that I get from tables, that's only valid at 298 degrees. That's how we calculate this, right? It's valid only at 298, so you cannot use this to calculate K. You can try using it, and you'll see that if you try using this equation at home, you're going to get a value that's quite different than the correct value that we got using the Van't Hoff equation. Any questions about this guy so far? We're almost done this chapter. We're ending with some fun, kind of chill stuff. Yeah? Yes. Actually, you know what? Yes, I will, but I'm going to add an extra slide at the break, and I will show you after the break, okay? Right. So sometimes we have a reaction that we want to happen, but it's non-spontaneous. But we really want it to happen, so what are our options here? What can we do? One thing we can do is change the conditions. Right? We saw, if you think way back to our example of water freezing, if I go and try to freeze some water outside right now, nothing's going to happen. But if I try again in the winter, where the conditions have changed, where the temperature is lower, then my water will freeze spontaneously. Right? So you can change temperature, you can change the pressure. Sometimes changing the conditions is enough to make something spontaneous. Another thing you can do is something called electrolysis, and this we're going to go over again when we get to the electrochemistry chapter, the last chapter of the course. So I won't get too into the nitty-gritty of it, but essentially electrolysis uses electric current to make a reaction happen. So we're adding an electric current to drive a reaction. And the third option that we have is what we call coupling reactions. So basically adding up two reactions together, where we can take a reaction that's non-spontaneous. So for instance here, A becoming B has a positive delta G value, which means that it is non-spontaneous. But if I add A to B with another reaction that is very spontaneous, right, this has a very big negative delta G value for B becoming C, if I add these two reactions, my delta G of the combined reaction through Hess's law can become negative, and we can make it spontaneous. And we can say that the second reaction that is spontaneous is going to drive that non-spontaneous one forward. So let's look at this with a more concrete example. So copper, let's say you have a change of heart in your life and you no longer want to be a scientist and you want to go become a miner, and you go down in the mine and you're mining copper. What you're actually mining is copper oxide, so Cu2O. But when we use copper in daily life, if you want copper pipe or you want copper wire, we just want pure elemental copper. So how do we get our copper ore here, copper oxide, how do we convert that into solid copper? Well, even if we change the conditions a lot, so this is what we want to happen. We want our copper oxide to decompose into pure solid copper and some oxygen. Even if we heat this up a lot, this little delta sign here over the arrow, that indicates that we've added heat, okay? Even if it's at 400 degrees, super hot, my delta G value is still 125 kilojoules, right? So we still have a non-spontaneous reaction, even at the super high temperature. So what is something else we can do? We can couple this reaction with something that is spontaneous, so that when we add them together, the overall reaction will be spontaneous. Right? So this is the reaction that we want to happen, right? We really want to take our copper oxide and make pure copper. We can add to this reaction a spontaneous reaction. So if we combined solid carbon and oxygen to produce carbon monoxide, this is a very spontaneous reaction. These are my, on the side here, are my standard delta G values. Let me just write that out. Those are my standard delta G values. If I add up these two reactions, my oxidants will cancel out because there's one on the reactant and the products. And I end up with this final reaction. It's not exactly the same as my initial copper decomposition reaction that I was hoping to have. Right, my final reaction here is not equal exactly to this, but it's getting the job done. My goal really was to get my copper oxide to be converted to solid copper. I don't really care that we're not producing oxygen in this reaction. As we saw with Hess's law, how do we figure out the delta G naught for this final reaction? I just add up the delta G naughts for the reactions that I've added up. So plus 125 minus 175 means that this final reaction has a delta G naught value of minus 50, and now this is spontaneous. And they actually use this in industry, and they use this method of coupling spontaneous reactions with non-spontaneous reactions. They use that a lot in industry. But does anyone have an idea where this is used the most? This is kind of a tricky question, coupling reactions, all of you biologists out there. Coupling reactions like this to make non-spontaneous reactions spontaneous is really, really important and really widely used in biological systems. So in our own bodies, in plants, in other organisms, they drive a lot of biochemical reactions. Can I get a show of hands? Who is going to be majoring or is majoring in some sort of biology-related program? That's not that many. I thought they would be, okay, no, there's a decent amount. The hands are just low. When I used to TA my first time here back in 2020, I would ask all my online students what they were majoring in, and I was like, I can't wait to be a chemist, and everybody was a biologist. And I was like, I hope you enjoy this bout of chemistry. So if this is the last chemistry you take, hopefully it's not too unpleasant for you. Anyways, this one is for you. So here's an example in a biological system. I'm sure you guys have seen all the memes of mitochondria as the powerhouse of the cell. It's kind of an old one. Maybe I'm aging myself once again. But why do we call mitochondria the powerhouse of the cell? We call it that because mitochondria make ATP. Can I get a show of hands if you are familiar with ATP? Just give me a show of hands if you know anything about ATP. I'm not going to call on you, I just want to see. Okay, a lot of you do, but some of you don't. You don't need to get too bogged down by the biology here. What you basically need to know is that ATP kind of acts as a stored form of energy that can be moved around in the cell and then used as an energy source elsewhere. Because ATP, when it breaks down, it releases energy. So the mitochondria make ATP, and then ATP moves around somewhere else, and then it breaks down and releases energy, gives energy to some other process. ATP, so adenosine triphosphate, that's what the T is formed from ADP, adenosine diphosphate. But the conversion of ADP to ATP, which is what mitochondria are trying to do, this is not a spontaneous reaction. So how do mitochondria do it? How do they get ADP to form into ATP? Well, they couple it with another reaction. So here's my cell. Blue squiggly is my mitochondria. They're trying to convert ADP into ATP. This is non-spontaneous, so what do they do at the same time? They convert glucose here, that's the C6H12O6. They convert glucose into lactate and some protons. This reaction that they're doing at the same time has a nice big negative delta G naught. This one is spontaneous, even though my conversion of ADP to ATP is positive. You don't have to get too bogged down here by the rest of the reaction. You don't need to memorize this. It's kind of partly for interest. But what you need to know is you have ADP here being converted into ATP. When I add these two reactions, my protons are going to cancel, and I'm left with this nice big overall reaction where ADP is becoming ATP and glucose is turning into lactate. And when I add up the delta G values of these two individual reactions, I get a negative delta G value for this final reaction, which means that, yay, the mitochondria have figured it out, and they can spontaneously now have this reaction happen where they're forming ATP. And then once the ATP is formed, it'll float around through the cell, and it'll get over here to the ribosomes. And the ribosomes, they need some energy to build proteins. So once the ATP gets over here, then the ribosomes are going to convert ATP to ADP. That gives them some energy, and they use that energy to convert amino acids or use amino acids to build up some proteins. Okay? That is it for thermodynamics. You've made it through what a lot of people consider one of the hardest chapters in first year chem. So good job. You're still with me and you're getting a lot of answers right today. Here are some suggested problems. These are just what I suggest, okay? And I was saying this to someone in office hours yesterday. If you are practicing the problems and you go through one of these guys and you're like, I know the answer now, so I kind of know how to do it, but I'm not feeling super confident, you can do the other questions in the textbook, okay? The textbook problems are really helpful. I just haven't listed, sometimes there's many different versions of sort of the same type of question. So just do as many other ones that aren't even listed here as you need to feel comfortable. Doing these practice questions and doing the practice tests that I've posted are going to be key to succeeding on your test coming up on July 22nd. Okay, so do lots of practice problems. Let's take a quick break here. Let's come back at about 10:20, and we will just briefly get into kinetics and just get excited about it so you can dream about it over the weekend. All right, we'll come back at 10:20.
So like I think we don't send it.
Okay, folks, just before we get into kinetics, based on our request here to go through the log calculations, we are ahead of schedule in lecture anyway, so let's quickly just go through this. So this is the question we just did, where we're asking for the equilibrium constant at 500 Kelvin. And so this I already showed on the board here, this equation, our Van 't Hoff equation. I didn't write out K1 just for the sake of clarity, I'll write out in a moment. I imagine you get to this step, and this is where you get stuck, right? So it's not so hard to get the math on the right side of the equation, but now how do we get rid of that ln, that natural log? Well, remember that according to log rules, and just stay with me here, the more you practice it, the easier it gets. E to the power of ln x, so x is just whatever number, whatever value we're working with, is equal to x. Now how does this help us? We're going to take both sides of this equation and raise them to the power of e. Because if I do e to the power of ln k1, k2 over k1, that's just going to equal k2 over k1. But I need to do what I do to one side of my equation, I need to do to the other side. So I'm going to raise everything to this exponent. When I raise the left hand, the ln side to the exponent, to e to the ln k1 over k2, I'm just left with, or sorry, k2 over k1, I'm just left with k2 over k1 after raising it to the power of e. On the right side of my equation, I'm left with e to the power of minus 0.4076. Okay, so you can just plug that e to the negative 0.4076 into your calculator. And then K2 will equal this value times my K1 value. So e to the minus 0.4076 times 5.51 times 10 to the minus 6. And now if you plug that into your calculator, you get a K2 value of 3.67 times 10 to the minus 6. There's other ways to solve this, right? There's other log rules where if you have a log of a fraction, like log of a division or log of multiplication, you can split up the log a different way. But this will always work. Whenever I get ln of something equals some number, I always raise everything, put everything to the exponent, e to whatever's on both sides, to get rid of my ln right away. Okay, so just sit with this if this is far back in your math memory. Any questions about this? Okay, great. Okay, just give me a moment and I will switch over to kinetics. Okay, so we've already gotten through all of thermochem, all of thermodynamics, and now we're going to move on to kinetics. So I mentioned this a little while ago that thermochem and thermodynamics really deal with energy, right? Energy transfer is something spontaneous, we look at entropy, but it hasn't talked about how fast reactions are. And kinetics is exactly as it sounds. We're going to talk about how to calculate rates of reaction and relate them to our reactant concentrations. So how does my initial concentration of my reactants affect how fast my rate's going to be? We're going to look at something called reaction orders. These give us some insight on how that reaction is progressing. We're going to look at integrated rate laws. We're going to look at half-lives, which are really important in a lot of nuclear research. We're going to look at the Arrhenius equation, which kind of tells us conceptually why do certain reactions happen faster than others. We're going to look at reaction mechanisms, which is almost like a little hint of a little foreshadowing of organic chem if you take organic chem in future years. And then we're going to end up with catalysis, with catalysts and different types and what they do and why they make reactions happen faster. So reaction rates, some are really fast, right? If you have a gas stove at home and you turn it on, you see as soon as you turn on your stove, the reaction is happening, right? We've got that natural gas reacting with the oxygen to produce a flame, and that flame has carbon dioxide and water being produced within it. And we see that happens as soon as you turn your stove on, right? Other reactions are super slow. So we talked a lot about rust in the course so far. Rust, of course, is just when iron reacts with oxygen, it makes iron oxide. Iron oxide is rust. And this might take months, this might take years for your bike chain or a part of your car to become rusty. What about this one over here? And we say that diamonds last forever, but technically, if you wait billions and billions of years, you have that kind of time on your hands, a diamond will actually turn into graphite. They're both carbon. But slowly over time, this will happen naturally. And I promise I will stop talking about thermodynamics, but this kind of makes sense. Because do you remember we talked about how the structure of diamond compares to the structure of graphite, even though they're both just solid carbon? If you recall, diamond was really, really ordered, right? Each carbon atom had 4 covalent bonds to other carbons. It's a really hard metal, and everything is stuck in an exact specific structure, right? There's not really much freedom of motion, and the entropy of diamond is really low. Graphite has a little bit more freedom of motion than diamond. Remember that graphite kind of stacks in layers. That's why our pencils rub off graphite onto your paper, because it's in layers. There's a little more freedom of motion, and we saw that graphite had a little bit higher entropy, a little bit more disorder. So it kind of makes sense that we would have something more ordered becoming something less ordered, an increase in entropy over time, right? Okay, well, I will stop now with thermodynamics. Now, in time, we are measuring the rate of something. What are we measuring? We're measuring the change in some quantity over the change in time. Okay, so I'll show you two different examples here of something with a slower rate versus a faster rate. And this might seem really simple and obvious, but what I've learned, having taken many courses in my life, when something is simple and obvious, just appreciate that it's not hard in this moment, okay? So here we have this reaction of A plus B giving us C, so the little blue rods and the red circles becoming C, which are these purple sort of oblong shapes. At time equals 0, we only have our reactants. After 16 minutes here, we've already used up 4 A's and 4 B's, and we produced 4 molecules of C. And by the 46th minute here, we have taken all of our A's and all of our B's and converted them all into C's. If we compare this with a slower reaction, here we have X plus Y equals Z. It's the same image really, but now in a green-blue color scheme. We see that in this one, at the 46 mark, we've only made 3 Z's and used up 3 X's and used up 3 Y's. This has a slower rate because we're not producing that Z as fast as we were producing up here. In other words, the change in Z over time, right? We've made 3, so the change as we produce 3 over time is less than the change in C over time. We've made 8 molecules of C in the same amount of time, so it has a faster rate. It's changed more in the same amount of time. Now, you can't get away from math in this half of the course, so how do we express this mathematically, and how do we work with reaction rates in terms of actual numbers, right? In terms of numerical values? Well, our rate, as I've been saying, is the change in some concentration over the change in time, right? Our little delta is our change. We can also write this, if you don't love the change symbol, this is equal to, oops, spoiler, my x concentration at time 2 minus my x concentration at time 1 over time 2 minus time 1, right? So if we have this reaction, we've got A plus B giving us C and D, we can rate the reaction rate, so the rate of the whole reaction, in terms of the change in a product or the change in a reactant. If we are looking at the rate in terms of the reactant here, so the one with delta A, we add a negative sign. The negative sign here, the sole purpose, is to make this as a whole into a positive value. By convention, anytime we are talking about reaction rates, unlike all the energy, heat, work stuff that we've seen, anytime we're talking about reaction rates, we are talking about them in as a positive value. You would never say the rate of reaction is minus 2.5 moles per second, okay? It's always positive. We say that the rate of consumption of A, because A is getting consumed in this reaction, so the rate of consumption of A is equal to the rate of production of C. if we think about the change in our reactant over time, delta A is equal to my concentration of A at time 2 minus my concentration of A at time 1. But A is getting used up, which means that my concentration of A at time 2, a little bit later in time, is going to be less than my concentration of A initially. Let's say I started with 2 molar A at time equals at the beginning of the reaction, and maybe at the end of my time point, now I only have 0.5 molar of A, which means that my delta A, my change in A, is going to be negative because it's getting used up, right? It will be minus 1.5 molar. It's decreased. Anytime you have a reactant, because it's getting used up, the change in their concentration will be negative, and that's why we add this other negative here just to cancel this guy out. Okay, so don't get too bogged down by the negatives when you're doing these questions. It's really just by convention to make everything positive. So if by chance you end up with a negative value, just make it into a positive. Okay? Let's look at this example. So here we have H2, that's this little white guy, and I2, this is big purple guy, becoming 2 moles of HI. Now the rate of this reaction, we can express it in terms of the concentration change of H2 over time. H2 is a reactant, so I'm going to add that little negative sign. This is virtually what I just wrote on the other slide. Or I can write it in terms of I2. This rate here, whenever we write rate, that is the rate of the reaction. It's the rate of the reaction kind of as a whole. Now what if I want to write the rate of this reaction in terms of HI? It has to have the same value as this, right, because there's only one rate for the reaction. But if I look at the stoichiometry of this reaction, every time I use up 1 mole of H2, I make 2 moles of HI, which means that my HI is getting produced twice as fast as my H2 is getting consumed, right? So I can say that my rate of H2 here, my rate of HI is equal to 2 times my rate of H2 because it's getting produced twice as fast. Or in other words, I can say that my rate of H2 is equal to a half the rate of HI. So how do I write the overall rate of my reaction in terms of HI? Well, I have to take into account the stoichiometry. I know that all of these need to equal the same value because they all equal the general rate of the overall reaction. So when there is a stoichiometric coefficient involved, we have to take it into account. Now let's look at this a little bit more formalized, okay? Here's our generalized rate expression. So my rate of my reaction overall is equal to, you can express it in terms of any of the reactants or products. So if I was doing this reaction and I knew I could measure B really well and I wanted to figure out the general rate of the reaction, I could figure out the rate of change of B and then multiply it by negative 1 over B to give me my overall rate of reaction. So what are some things to note here? Every time I have a reactant, I put a little negative sign in front of it. And anything that has a stoichiometric coefficient, we're going to have to divide by it or do 1 over the stoichiometric coefficient. And now in all of these, they should spit out the same value. Okay? This might be a little bit easier to look at in a practice problem. We'll just get through a couple more slides and then I'll let you go. This question says, the Nitrosomonas bacteria convert ammonia, that's NH3 here, into nitrite, which is HNO2, in the presence of oxygen according to this reaction. So it's asking us to write the rate expressions to answer the following. How is the rate of formation of HNO2 related to the rate of consumption of NH3? And how is the rate of consumption of NH3 related to the rate of consumption of O2? In that previous example, we saw that the rate of HI production was 2 times as fast as the rate of H2 consumption. So this is really asking us the same thing. And this one I think I will just go through right away. So when you have a question like this, right away just write out the generalized rate expression. So my rate of reaction is equal to, okay, so let's look at my NH3. NH3 is a product, so I'm going to add a negative, or sorry, it's a reactant, so I'm going to add a negative. It has a stoichiometric coefficient of 2, so I'm going to do 1 over 2 times the change, times the change in concentration of NH3 over time. And that's going to equal, right, now we've got to look at our HNO2. It's a product, so we're not going to add a negative, but it also has a stoichiometric coefficient of 2. So I'm going to have to divide by 2 times the change in concentration of HNO2 times the change over the change in time. These are equal to each other, so my 1/2s are going to cancel. And what am I left with? Well, the rate of consumption of NH3 is just equal to the rate of production of HNO2. Now, you don't have to write this out if it's not explicitly said. You could just logic this out, right? I see that they have the same stoichiometric coefficient. So every time I use up 2 moles of NH3, I'm producing 2 moles of HNO2. And by that logic, since 2 are used, 2 are produced, they're being used and produced at the same rate. Now, question B is a little bit trickier. Now we're comparing NH3 and O2. These do not have the same stoichiometric coefficients. So let's approach this the same way, where I'm writing out my overall rate of my reaction is equal to minus 1/2 the rate of change of NH3. That's the same as we wrote in the first question. Now what about oxygen? Well, oxygen is also a reactant, so I'm going to add in a little negative. The stoichiometric coefficient here is 3, so I'm going to divide by 3 times the change in concentration of oxygen over the change in time. Now I want to figure out how the rate of consumption of this guy relates to that of oxygen. So I want to get my delta NH3 over delta time. I want to get it alone on one side of this equation. So how do I do that? Well, I'm going to multiply this whole thing by 2, right? I'm going to multiply both sides of the equation by 2. I'll put my little therefore sign. My change in NH3 concentration over my change in time is equal to 2/3, right? Because I multiply both sides by 2, the rate of change of oxygen over time. So we can say that my rate of consumption of NH3 is 2/3 the speed, or 2/3 as fast as the rate of consumption of oxygen. Now, anytime you have a question and you get to your answer, ask yourself if it makes sense. My rate of consumption of NH3 is 2/3 that of O2, which means it's not quite as fast as the rate of change of O2. Does that make sense? Yeah, let's go back to our reaction here. Every time I use up 2 moles of NH3, I'm using up 3 moles of oxygen, which means that I'm using up more oxygen every time I do this reaction than I am ammonia. It means my oxygen is getting used up a little bit faster. My NH3 is getting used up a little bit slower than my oxygen. So it's 2/3 as fast. It's like 67% the speed or the rate of the oxygen consumption. Okay, grab out your phones, take out your phones, and give us a scan. This is going to be our last slide for today. So we'll just get this guy in, go through this question, and then you will be free to go. So this question states that H2O2 is hydrogen peroxide, can be used as a disinfectant, and it decomposes in this reaction. So H2O2 decomposes to give us water and oxygen. If the rate of appearance of oxygen is 0.0014 molar per second, what is the rate of disappearance of hydrogen peroxide? And you can either calculate this one, or you could probably logic this one out. Okay, I'm just gonna give this like 5 more seconds. Then actually, I want to go back to one of the earlier slides for 2 seconds at the end, so don't pack up just yet. Okay, folks, last chance to get your answers in. Panic. Okay. So we're getting mostly C, which is correct. If you want to just logic this one out, we see that the rate of appearance of oxygen is 0.0014. Every time I produce 1 mole of oxygen, I have used up 2 moles of hydrogen peroxide of H2O2. That means my H2O2 is being used up twice as fast as my oxygen is getting produced, which means that the rate of disappearance of H2O2 is just twice as fast as my rate of oxygen, so 2 times 0.0014 molar per second, which is C. If you wanted to write this out, and sometimes it's helpful to know how to write it out because it's not always super obvious. I can write out my rate, right? So my rate is equal to my change in oxygen. It doesn't have a coefficient, right? It just has a coefficient of 1, which is equal to minus a half times the change in H2O2 over change in time. If I multiply both sides here by 2, I've got 2 times the rate of change of oxygen is equal to my rate of change of H2O2. And I know that this, here, my rate of appearance of oxygen, is equal to 0.0014 molar per second. So it's just going to be 2 times this guy. Does that make sense? Okay, try to sit with it. Come to office hours. I have them today if you are around and have questions. One thing I'm so sorry that I wanted to mention that I forgot to. When we're dealing with the rate is always in units of molar per second. It's not moles per second, molar per second. That's moles per liter per second. So another way that we could write that is moles per liter times seconds. It's the same way. Or you can write it moles times liter to the -1 times seconds to the -1. These are all the same. It's important that you know how to write out the units, and you can go between these different ways of writing it, where you have just a big M for moles per liter, or you actually have moles and liters written out, and you also know what the negative ones here. You need to be able to go between these 3. This is important, okay? Do with that what you will. You need to know your units. Okay, thanks, folks. That is all. Have a great weekend, and we'll see you back here on Tuesday.